your setups to mine. I am going to pick this up. This is going to be a quick, easy 100 for like, oh, most of you. Yeah. Okay, what I care about are your setups. Are you showing me where the work is coming from? Right, this first one, when you come up with your estimate of 30.615, there is no work to show. Your calculator does the work. Let your calculator do the work for you. However, when we start getting to the approximations with the different methods, now you don't have to write A1 plus A2 plus A3 plus A4. That's not necessary. What I have to see is this stuff. Right, 1 times f of 0, 1 times f of 1, 1 times f of 2, 1 times f of 3. Do you need to show me the 1? Not really. You're multiplying by 1. It's okay. Anything else that you're going to multiply by, I need to see it. And hopefully you get 31.099. Okay? All right, part C, the estimate is an overestimate because the rectangles contain more area. Something to that effect works for me. How could you make the approximation better? David, what would you do?
More rectangles.
More rectangles. The answer is always going to be more. Give me more. Give me more rectangles, more trapezoids, more of your attention. Wolverine, focus. All right, 2. Okay, now I'm being sneaky. I'm changing the limits of integration on you, and you better be ready for it. 35.033. Okay, and A1, A2, A3, A4, A5. Uh-oh, shame on me. Shame on me. I started with f of 1. I did not mean to start with f of 1. F of 2, F of 3, F4, F5, F6. 33.626. Oh. Now I'm getting an underestimate. Okay, and now in 2D, now I've increased the number of rectangles, so you're going to do 10 area computations. Gosh, it would be really helpful here to know that that 1/2 is a common factor and factor it all out. You're not wrong if you forgot to do that, but oh my gosh, it makes the computation faster. So on and so on. And I don't think on this one I actually wanted you to do the computation, I just wanted the setups. Is everybody feeling really good about this? Maya, are you okay? As long as you're okay, that's all that matters. Okay, everybody else, just kind of get in the way. All right, so next one, we're gonna check number answers here. 3A, 50.506. Okay, 3B, 61.271. 4A, 47.931. 4B, 37.112. Of course, I need to see the setups. Palomon. Oh, I know what that looks for. Okay, good. And that's that. So if you could just put your name on it, put it in the middle of the table. Really, I'm going to spend like 10 minutes looking over this, giving you some feedback, making sure that all the teenagers did all the right things. Maybe I need to have another tough conversation. It seems to not be sticking anymore. Hi, Myra.
Method 4B.
4B. You can see anything you want because you're a friend of Celeste and I'm terrified of her.
You're welcome.
37.112 or 37.113 or Celeste, whatever you have on your paper.
Okay.
All right, everybody good? What I hope, what I expect is that in the world of Riemann sums, things are good for everybody right now. The purpose for the rest of today, the next 28 minutes, I want to push your thinking. I want to push it further. You will not use your calculator for any of these problems. Lewis is he's like doing the wrong thing these days. He's like, I got my, oh, don't need my calculator. You're not going to need your calculator, you're going to need your brain instead. Oh, man. I know some of you guys forget that at home. All right, so please put your homework in the middle of the table. Tonight's homework, Lewis, what are we turning in tomorrow?
Corrections and
the test corrections and the test reflection. For those of you that are staying after school with me today to work on those corrections, do them well. Give me a reason to change that test grade, to be a little bit gracious and have the grade go up a little bit. If you don't stay, you don't have that opportunity. Okay. All right. The other homework assignment that I need you to know about is in the problem set. And I'm so excited. I recreated this one. Made it a little meatier because you guys deserve the best all the time. This is it's assignment number 72. Okay, Philemon, you probably want to jot this down somewhere. There is a front and back, Both parts are due Friday. Okay, the reason I'm giving this to you now is that some of you don't really have a lot of corrections that you need to do on the unit test. The smart thing to do would be to start it tonight. This is a long assignment. It's probably going to take, even the 11 of you, about an hour to get this done and do it well. So if you can start on it tonight, why are you dropping the mic on me? Boom.
David
Okay.
can do it.
It's all Riemann sums. It's all calculator active. It's the stuff that we've been doing. It's just now in a context. But I want you to start it tonight so that tomorrow night you're not in like freak out mode.
No, I'll probably do it today.
Or Friday morning. Okay.
Oh, I'm grounded.
You're see you're grounded?
Yeah.
Oh, that sucks. All right, so here we go. Let's look at some problems without the calculator. Steve, you have the friends at North Central and East End online?
Yes.
All right, so we're going to do the first two together, and then you guys are going to partner up. Somebody does have the pleasure of talking to these good-looking teenagers on the other side of the camera.
Wait, where are we at?
Okay, we're on page number 18, round 1. 18, round 1. Have a strategy conversation with somebody near you. Without using your calculator, I want to determine the exact value of the integral from negative pi to pi sine of x dx. Have a 1-minute conversation. What are you going to do? I'm going to take attendance. You get no calculator. Yeah, I'm taking attendance, I know. Alright, so I don't see Giselle. If you get number 1 under control, move on to number 2. We'll talk in a second. And I don't see Alright, somebody tell me, how on earth are you going to figure out the definite integral from negative pi to pi sine of x dx? What would you do? Let's start with that better question. What am I even looking for? Lewis, what am I looking for?
the area between the pi and
The
negative
area
pi,
between
the sine
the graph of the sine of x
on interval from negative pi to pi.
from negative pi to pi, the area between graph of sine of x and the x-axis from negative pi to pi. And I hope you guys all remember what the graph looks like. Graph looks something like that, and because it's a periodic function, it does something like that. Negative pi is over here. Positive pi is over here. How would I ever find that area without my calculator? Lewis, what's the thing I need you to know here?
That since from 0 to negative pi is negative area, and
From 0 to negative pi we have negative area. From 0 to positive pi we have
positive area.
positive area. Now here's the thing I want to be careful about. Because some of you guys are going to be tempted to say 0. And I'll say 0 is 100% the right answer. But why? I need to know something really precise here. Polymon, what's the why? Why is this 0?
Since the values are the same, and one is negative and positive, they cancel out.
The values are the same. One's negative, one's positive. You're saying like the value of the area is the same? True, but there's something special. There's a word I haven't heard yet. There's something about the function. There's something really special about the function that you may not remember from pre-cal. It has to do with the fact, it has to do with the symmetry of this function.
Think of an adjective to describe it.
Symmetrical.
There is some symmetry, but normally when we think about symmetry, you might think about x-axis symmetry. Is that what we have? Y-axis symmetry? Y-axis symmetry? There is no way we have y-axis symmetry here.
It's the angle.
Not that, it's called rotational symmetry. If you were to like put your, I always think of the origin as like the belly button. If I put my finger in the belly button and I spin this graph, this guy here goes exactly over here, this guy here goes exactly over here. They are going to be equal and opposite because the sine, the word that you guys were looking for, is it's an odd function. Odd functions have rotational symmetry. All right. All right, number 2, which is greater, the integral from 0.1 to 10 of the natural log of x or the integral from 1 to 10 of the natural log of x with respect to x? Be ready to defend your answer. One of them is greater, but what I care about is the y. How many of y'all would say the integral from 0.1 to 10 of natural log of x is the one with the greater area? I see 3 people, 4 people, 5 people. Okay, how many guys think the area from 1 to 10 of the natural log of x is the greater? Lewis thinks this one is also greater. You voted twice. And a lot of folks have not voted at all. What does the graph look like? What does that graph look like, Myra? It looks like, really? No. That's not what the graph of the natural log of x looks like. You want to pay attention to what Lewis is doing over there. Now be careful because I see you doing this thing and you might be like, oh, like square root. No, no, no. Not like square root. Like this guy here. The important thing to pay attention to with this graph is the root. Where's the root for the natural log of x graph? There's a vertical asymptote at x equals 0, but where's that root? Said another way, when is the natural log of x equal to 0? I know you guys know this. Natural log of what number is equal to 0?
Negative.
Oh, awkward. So if you're not sure, the way that you would solve a problem like this in pre-calc, you exponentiate both sides so that that guy cancels out, and x equals e to the 0, which is 1. So the root is over there. Take 30 more seconds, talk to somebody near you. Which one's bigger and why?
That one.
Which one's bigger and why? We've got the graph of the natural log of x. We've got a root at x equals 1. Choices are 0.1 to 10 or 1 to 10. All right, friends, let's check in on this. How many of you guys think the first one is greater, the integral from 0.1 to 10? Nobody. And how many of you guys think the one from 1 to 10 is greater? Everybody. Okay. I want to hear from somebody who switched camps here. Why the first time would you say this one is greater? Polymon, what did you see?
It's well, we had the thing switched. So we thought it was going.
No.
That's not what I thought.
That's not why you thought it, Celeste. Why did you
Because it was a greater, on a greater interval, so I thought it was more.
Right, that distance that we're covering with our area from 0.1 to 10 is greater here than it is over here. Like I set you guys up to get this one wrong. Okay? So you're like, it's a bigger interval, but the mistake, David, what's the mistake that those folks are making?
Well, I make the same mistakes.
Yep.
I thought that I didn't remember that graph looked like this.
Yeah.
So I thought like the point 1 was gonna be like on the positive side.
Right. But with x equals 0.1 being over here and x equals 10 being somewhere over here,
We had negative and positive.
you're getting negative area, which takes away from whatever positive area you would be thinking about. This guy here is positive area only. We got how we're going to play the game here? All right, you've got the next 3 minutes to work on problems 3 and 4 with somebody you are not currently sitting with.
Armin.
Whoever partners up last, you get the camera.
Steven, I'll get you next time, Steven.
No, I got it next time.
They're all from the same thing.
Yeah,
I
you guys
think
are all
when
from
we
the
do this,
same
I'm
thing.
going to put like a picture of some friendly, good-looking teenager over here to make it easier for Steven to have a conversation about 3 and 4 with your friends. You do you. You do you. But have some conversation with him.
All right, so for number 3, you're gonna
That's the equation we use
find the antiderivative of e to the x power. So,
Oh, that will not help you at all, Stephen.
oh, I have not read it.
What did he say?
Ignore Stephen. That's what he said. He said, ignore me.
Which is greater?
Wait.
I understand what you're doing. You're trying to find an antiderivative and you're going to evaluate the endpoints. That doesn't help here because I'm not asking for the exact value. I'm asking for a left endpoint approximation compared to a right endpoint approximation.
The greater one is,
Because look, we don't have it.
it has to be
So like
right.
if-
Because right, endpoints are always.
That's not true.
But this one would be right.
Right, it's not just about the method that we use, which one's bigger. It depends on the graph in combination with the method.
How do you get like?
On the right hand curve, that's what we like.
Really? With all that big brain stuff happening, the graph of e to the x looks like this. Yeah. You've got a horizontal asymptote at y equals 0, passes through 0, 1, increases.
I'm gonna give it.
Oh, okay, well, we need to.
And this is why people say mean girl.
What? No one says that.
Yeah.
It's okay down there, it's increasing in the
Because
It's increasing.
Left x is positive.
Yep.
And increasing.
It will be the right endpoint method or approximation that it will be like rectangles will have more area because
Alrighty, friends. Sorry, Stephen, to interrupt your conversation. All right, so number 3, which one's going to be greater, left endpoint approximation or right endpoint approximation? How many guys went with left endpoint approximation as the greater one? Nobody. So everybody went with right endpoint approximation? Everybody feels good about right endpoint approximation? Andrew, you feel good about your right endpoint approximation?
Yeah.
Why did you guys decide right endpoint approximation?
Oh, we didn't choose.
Because what?
Oh, we didn't choose yet.
Oh, you didn't choose yet. Bummer.
Yeah.
So we've got the graph of e to the x on the interval -1 to 3. Why is the right endpoint approximation greater? Think about drawing some rectangles here. David, why is it going to be greater?
Because when we do the right endpoint,
Yep.
it will go over, like, over there. So,
Now, did I tell you how many rectangles?
No.
We didn't even talk about the number of rectangles, but no matter how many rectangles I draw, however I partition my interval, right endpoint method says go up to the curve, over, down, over, down, over, down, over, down. Overestimate to the true area, right? If I tried the left endpoint approximation with the same graph, and we say, okay, here's x equals -1, here's x equals 3, if I partition that interval, left endpoint up, over, down, up, over, down, up, over, down. This guy's giving me an overestimate to the true area, whatever it might be. This one gives me an underestimate to the true area, whatever it might be. This guy has to be greater. All right, next one. Let it be a function which is positive, increasing, concave down. If A is less than B, which method must generate an overestimate? First of all, can you guys draw in the air for me a graph that is positive, increasing, concave down? Positive, increasing, concave down. All three things. All three things are going to have to look like something like that. Okay? So here's x equals A. I don't know where x equals A is. I don't even care. Here's x equals B. All right, which must generate an overestimate? Has to generate an overestimate. Let's get some hints on this. What do we pick? What do we pick? Give me one of the methods that you're sure is going to give you an overestimate. The right endpoint method? Is everybody okay with that? When I draw my rectangles, I'm going to go up, I'm going to come over, I'm going to come down. I'm going to go up, over, down. The right endpoint method for sure, which I'm going to abbreviate as REM. Left endpoint method? Nobody's going for left endpoint method. Left endpoint method, think about drawing some left rectangles here. They're all going to be underneath the graph, underestimate. How about midpoint method? Is that not one of the options I gave you guys? Okay, good. How about trapezoids? With the trapezoids, and here's the thing you want to be careful about, draw them. If you actually drew some trapezoids, what you notice is going to be an underestimate. All of these guys here, this part over here, these are actually, I just want to get some fancy vocab going in there. It's a line segment, but it's a special line. It's a secant line. And we know something about secant lines and their relative position with graphs that are concave down. Secant lines are under the graph for concave down. The kind of line that's above the graph for concave down would be, what kind of line's above the graph for concave down? Tangent lines are above the graph. Tangent lines would be overestimates. Secant lines are below the graph. Secant lines are going to generate underestimates for the area. So the only one that's going to work here, right endpoint method. Pretty good? All right, new partners. Show me what you can do. In round 2, we're not going to do all the problems. I'm interested in what you guys can do with problems 7 and 8. Problems 7 and 8. We'll talk in 3 minutes.
7 and 8. Electric wall.
Hello, Lewis.
Lewis, we can do
7 and 8.
Loose.
7 and 8.
Face the camera loose.
So,
At least he's talking to them.
True or false for all of the values of A.
Alright, so for my friend Lewis. Alright, all values of A with A greater than 0. The integral from negative A to A of sine of x dx is equal to 0.
I think that's true.
You think it's true? Tell us why.
Since A is the same number,
Yeah.
you can like plug in pi and then like it's like number 1.
Yeah.
You got 0 because like they're the same letter. Because they have negative area and like they cancel.
Okay. So the graph of sine of x is an odd function, so maybe like you've got a quick sketch of it. Okay? And if I'm going to go from negative A to A, however far left I go on the sine graph, I'm going to go that far to the right on the sine graph. And that graph is an odd function. And so what should always happen is you're going to have some cancellation.
The areas should always cancel each other.
The answer is the areas are always going to cancel each other. Having the graph in front of you makes it a little bit better. Alright, so what you can do in the break. Okay, friends over here, we don't go with the Are we comfortable with 0? Because it is an odd function. Okay.
No, because this is probably.
How are you feeling about number 2?
Oh no.
Okay, number 7 is period of the two things are happening.
Yeah.
That's our solution. It is 5. But I went right pi over 2. Then you don't have like balance on the sides of the line. That's not. Oh wait, no, that's not the cosine of x. That's the negative of the sine of x. All right. I think it's about time. Yep, it's about time. All right, sine of exercise. Just about everybody had this on their paper. Now, here's what I'm a little bit worried about. I see this graph a lot, which is true, and I think you guys are thinking, oh, just like that first one when we went from negative pi to pi. True, just like it, but this one's stronger. Right, this is a stronger statement. I'm not saying just from negative pi to pi. I'm saying for any value of a that I pick. Meaning go as far to the right as you want to go and go as far to the left as you want to go. Will you always have cancellation? Like what if you only went that far and you went that far left? Will those areas cancel? Right? What if I went out further? If I think about the periodicity, if you want to like get all fancy, of the sine graph and you went like way far out and you go the same way far out this way, you're still going to get all the canceling. Everybody okay? So this one is true. I just want to make sure we're thinking about more than just that one example. Cosine of x graph, assuming you've got that sketched correctly, looks something like this. And I think as soon as you guys sketch it, you know exactly what the answer to this is. This has to be false. This has to be false. All right, new partners, 2 new questions. Let's make it happen.
No.
All right, this time, I am interested in numbers 9 and 10. 9 and 10, 2 minutes. And somehow no one's talking to the friends at North Central and East End, and no one moved. The only movement was Lewis moving out of the camera. That's okay, the camera can come to you. 9 and 10, make it happen. See what happens, bunch of cheaters?
They cheat too.
No, but you guys are better looking, so. Thank you. And now Lewis is right. You cowards.
Function and like we use a trapezoid function to make a value that will the estimate be an overestimate or an underestimate.
No.
It was
Oh, 1. No, negative 1. Negative.
It's 1 to 5.
Oh, this is a dimension.
so 1 over 5 so it'll be on this side. It should be
Yes, we've got the right graph, we've got the right interval. Think about your trapezoids. Make some trapezoids here. Alright.
so it should be 100 right now.
Oh, no, I'm sorry. I was pointing to the stickers on the wall.
Yeah, I left mine too.
Oh, sorry.
Whatever. I figured it out.
Wait, why are you saying 1 minute?
I'm curious, so number 9, how many of you guys are going for underestimate? How many of you guys are going for overestimate? How many of you have no idea how to decide? Thank you for the honesty. So we've got the graph 1 over x from 1 to 5. Make some trapezoids. Heck, just make one big trapezoid if you need to. One big trapezoid looks like that.
No, crap. No.
I just did it based on what you told me before about the secant lines.
Right, or if you're like, no, you mean multiple trapezoids. Yeah, I mean multiple trapezoids. Overestimate. David, you were just impressing the heck out of me there. You're like, I just did what you just talked to us about, which was what?
You said that if it's concave up,
If the graph is concave up,
and then the secant lines will be over.
the secant lines are going to be over the graph, because what's going to be under the graph? Tangent lines are under the graph if the graph is concave up. Secant lines are over the graph if it's concave up. The secant lines and the tangent lines are going to give you a different kind of estimate. Tangent lines here below the graph, secant lines are going to be above the graph. Alright, now we're getting me in the graph of 1 over x squared. Well, that's that little like volcano thing. There we are. Lewis is just a man on the move. He's got people to see. From -5 to -1? Okay, trapezoids, make some trapezoids. Guess what kind of estimate we're getting here, friends? If I'm going to go from -5 to -1? Overestimate. The graph is concave up. Concave up. Your secant lines are above. Stephen?
Wouldn't it be an underestimate because it would be a larger negative area?
But look at my interval. My interval, I'm going from -5 to -1. I'm going left. Direction matters. From -5 to -1 would be positive. You're thinking if I was going from -1 to -5?
That one.
Right. I'm going from the left to the right, which is the correct direction. Alright, homework tonight, that's due tomorrow, Lewis. Unit 4, test corrections and reflections. See you later, come on in.
I forgot what